Hello, and welcome to our first session on combinational logic, where we'll look at coming up with the sum of products expressions for digital logic functions. Combinational logic can be used to implement a wide variety of functions, including those associated with arithmetic, such as addition and subtraction, to transmit data from one form to another, such as serial to parallel, or to convert one code, one way of expressing information in ones and zeros, to another. The sum of products expression allows us to express all the information contained in a Boolean function or in a truth table using first AND functions and then OR to come up with the sum of products. The truth table can contain one of three states: a 0, which represents a false or a low, a 1, which represents a true or a high, and finally, the truth table can also express X's or don't cares, which mean that it doesn't matter what in that particular entry in the truth table is a 0 or a 1. It can be assigned either as a 0 or a 1, depending on what is most convenient to obtain the most efficient digital logic implementation possible. Let's take a look, though, now at the sum of products expressions for digital logic circuits. In this truth table, we'd like to express the sum of products doing an AND, then an OR in our Boolean expression for this truth table. To do that, we'll take a look at the ones in the truth table. And for any entry that produces an output of 1, the variable contained in that entry, if it's a 0, we'll express it as its inverse in the sum of products expression, and if it's a 1, we'll express it in its uncomplemented form. So that means the expression for this first line of the truth table, which produces an output of 1, will simply be x0 and y0, because both x and y are equal to 0. The next term in the truth table that produces a 1, x is 1 and y is 0, so we'll express that as x and y0. And finally, the last line in the truth table that produces a 1, the fourth line, x is equal to 1 and y is equal to 1. So the term that represents that in our sum of products expression will simply be xy. Now we can simplify this expression once we have it using Boolean relationships that we've used before. And here we'll just pull the y0 out of the first two terms, get x bar or x, or xy, which will give us y bar or xy. Since x bar or x will simply produce a 1, and then any variable ANDed with a 1 will produce that variable. Then using the consensus law, we can see that this expression here is simply x or y0. And that's our simplified expression, although we started with the basic sum of products expression for the output to get to that point. Once we've simplified x or y0, we can implement it using De Morgan's theorem and only NAND gates, as we've discussed in previous implementations. X or y0 gives us this implementation using an OR gate, and to convert it to a NAND gate, we now need to invert the inputs to the OR gate, but in doing so, we need to make sure that we don't distort the value of the output, so we have to add extra inverters. There's a double inversion going on, and these two will cancel out. But from De Morgan's theorem, we remember that an OR gate with an inverted input is simply equal to a NAND gate. And then x still has an inversion associated with it, so we'll leave the inverter there for x0 coming into the NAND gate. And y now has two inverters, which will cancel out, leaving only y. And this is the NAND gate implementation of the original function we had in our truth table in this example. In another example, now with 3 inputs, we can see in this truth table that we have 5 lines in the truth table that result in an output of 1. That means that we expect in our sum of products expression that we'll have 5 terms. And to come up with those 5 terms, we'll look at every line in the truth table. This second line of the truth table produces an output of 1, so it will generate a term in the SOP expression equal to x naught, y naught, z. This next line in the truth table will produce a term x naught, y, z. The next line will produce x, y naught, z. Then x, y, z naught. And finally in the last line of the truth table, x, y, and z. To get the final expression for out, we'll just OR all these terms together. X naught, y naught, z, or x naught, y, z, or x, y naught, z, or x, y, z naught, and finally or x, y, or z. And this will be the complete sum of products expression for this particular truth table. Let's look at a word problem. So we'd like to understand or to find an expression for the warning light in a car, in the dashboard of a car that turns on, or it becomes a 1, when one or more of the doors is open. And in this truth table, we've expressed the function of the warning light for a 4-door sedan. So we have 4 inputs, door 1, door 2, door 3, and door 4. And it's always equal to 1 when at least one of those doors is open. Now this gives us 15 lines in the truth table that produce an output of 1, which would produce an output expression, sum of products expression, that has 15 terms. Surely there must be an easier way. And there is. Let's think about what's going on here. We know that the warning light is going to turn on whenever door 1, A, or door 2, or door 3, or door 4 is open. So in this case, we've been able to come up with the expression just using common sense and taking a look at the problem statement. That was a lot easier than going through the whole sum of products expression and simplifying it. In this next example, let's see if the sum of products expression shown here is actually accurate for producing the output C out. To do that, we'll look at each term individually and then OR them together. So the first term is A and B, which is only high when both A and B are equal to 1. And that gives us mostly zeros except the last 2 lines of the truth table here. In the next column, the next term ACN is calculated, which is equal to 1 only when A and CN are both equal to 1 at the same time. And again, that gives us mostly zeros in the truth table. And finally, the term ABCN is equal to 1 only when all the inputs are 1, which occurs only in the last line of the truth table. And now ORing all these together, do we come up with what's given for C out? In the first line we get a 0, that's accurate, then another 0, then another 0, but 0 or 0 or 0 is equal to 0. This truth table is therefore incorrect, even though the rest of the truth table appears to be accurate. So this sum of products expression does not actually express this truth table. So in this session, we've looked at the sum of products, and it's an accurate, straightforward, and reliable way to produce a Boolean function from a truth table. The sum of products lends itself naturally to an AND, then OR implementation of the truth table, which can be readily converted to a NAND-only implementation in just a few steps. This is very valuable in minimizing the real estate, the power consumed, and maximizing the speed of Boolean functions when implemented in digital logic circuits. Well, that's all for Sum of Products today. Thanks so much for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.